Uh, uh, Good evening, everyone. Am I audible to you all? Can anyone confirm in the chat box or by unmuting yourself? Am I audible to all? Okay, so I think let's start our this live session of this NPTEL. So let me share my slides. So welcome you all once again for this live session of NPTEL. The course name is Solar Energy Engineering and Technology, and this course is being run by NPTEL. So, the course instructor is Professor Pankaj Kalita. He is an associate professor in IIT Guwahati. Okay, somebody wants to join. Anyone else? No. Okay. Okay. The course instructor is Professor Pankaj Kalita, and he is associate professor in IIT Guwahati. I am Rohit. I am a PMRF scholar, and I will be taking this live session for this course. Join. Okay. So let me start with my introduction. So I am basically a research scholar in IIT Bombay. So this course is basically designed for the students who wants to gain knowledge about the solar energy. So there are various principles related to energy that you need to know. Apart from that, how solar energy can be harnessed by us, like in the form of solar photovoltaic cells or in the form of solar concentrator. So this course is specifically designed so that you can have a good knowledge about these things. So why this live session is there? So live session is basically to enhance the interaction between the students and the course content material and the instructor. So you see if anyone wants to join. Okay, nobody wants to join. Hmm. So this live session are basically to have an interaction with the students of this course. So if there are any queries which you have which may arise during when you go through the lecture of this course or anything you want to ask, so we can discuss those queries. We can find answers to those questions. If I know the answers, I will give the answer straight away. Otherwise, we'll discuss them in the next class. Okay. So don't worry, I will give most of your queries will be satisfied in this live session. And if there are some queries which need some introspection or interaction with the related literature, then I will take those queries forward in the next session so that all of you can benefit from those queries. Okay. So what I say ki please go through the course contents which are uploaded on the NPTEL website, and if there is anything you want to discuss, so we can discuss them in the live session itself. That will also help you to gain a grasp the course from its basic, and if anything you want to understand a better in a better sense, then I can help you understand by teaching it again, or we can have a discussion on those things. So this is what I am planning to have in live session. So for this live session, what see if somebody wants to join. Seems like students are joining so late. So I will give a suggestion to all the students. Please join by 7:05. So generally we will give a buffer of 5 minutes so that everybody can join. So it helps me to make a flow for this course because every time the student join, I will have to go back and let them admit. So I think that will help all of us also. Okay. The recording is on. So what I have for this live session, what I have planned that key I will discuss the old assignment questions, the assignment from previous, the questions from previous run of this course, like week zero questions, or I will go through these questions one by one. Then we will discuss. In between, I will also show the slides of this weekly content, so we can have a discussion also, and then we will have an interaction, one-to-one interaction with the students, where the students can ask questions to me and I will be able to answer most probably all the questions will be answered. Okay, so once again welcome you all to this live session. Let's start our course. So I think before we go to this assignment questions, I think it will be good if I go through the revision of the course so that will help you guys to get a grasp of this course also, because I am sure that most of you haven't gone through those slides, so that will also help you to have a revision. Okay, so I have opened this slide here and we will have. So this is the module one which was uploaded for the week one. So it basically talks about the introduction to the solar energy. Okay, so I think here the professor had discussed what is energy. So many of you may not have engineering backgrounds or a science background. Many of the students can be from arts or humanities background that they wanted to learn about the solar energy. So for them we have started it from the basic, bare basic itself. I think someone have unmuted their mic. Marulia Begum, do you want to ask something? I think he has done it by mistake. Okay, so let's see what is energy. So energy is defined by somebody is putting his mic. Marulia, do you want to say something? Uh, okay. So everyone, please make sure that you are muted because it makes a disturbance in between the course. If you want to ask something, please raise hand, or you can unmute, then ask the question. Okay. So that is totally okay. Okay. Students are joining again and again. So what is energy? So most of you have very familiar with what is energy. Energy is something which defines your ability to do work. But to define something as energy, you need to understand the concept behind energy. So, as if we say energy, energy is basically some capability to do work. Okay, so if you want to place this big table from here to there, so you will need energy. Okay, So this basically the capability to do work basically depends on the amount of energy that one can control and utilize. Okay. So you can control the energy, like the flow of water has kinetic energy. So you can control the kinetic energy by building a dam. You can control potential energy by raising the height of the object. Okay, so if height is lower, then the potential energy will be low. So it is totally okay to control the energy. Energy can be controlled and utilized for our purpose. It can be converted from one form to another also. So generally, why do we need energy? What is the main basic purpose of having talking about energy? So energy is important, but to get work out of energy is the main thing. Okay, so whatever we do work, whatever we put as input, then we get as a output. So that difference is called del W. That is change in work output and input. So that is the main thing which we are interested. Okay? And energy is basically the most basic infrastructure input for economic growth and development of the country. So if you talk of the economic growth, so we have underdeveloped countries, like if you take an example of underdeveloped countries like Bangladesh has if you see a per capita energy consumption of Bangladesh, that is much lower than what India as a country is consuming. And if we compare India with some highly developed countries like US, UK, so you will see that US, UK are consuming much more than what India is consuming per capita. So I will give you an example also. The per capita electricity consumption, electricity which is a part of energy. So per capita electricity consumption is basically 1 kilowatt um, per capita per human consume 1 kilowatt hour of electricity. So if we compare this data with US, that is something around 20. So it's 20 times more electricity consumption in the US. So it basically depends on the economic growth of the and development of the country also, because US is highly developed, then have uh, quite huge number of industries. They have quite huge number of industries, so they require a quite big amount of energy this for feeding their industries, for running their day-to-day industries. So and the level of consumption of electricity is quite high for these high developed countries compared to the low developed countries or compared to middle income countries like India. Okay, so this is the main crux of the requirement of energy, which is uh, think or thought of when we talked about energy or talk about energy. So I think most of you know that key unit of energy is joule. So it's quite common. We learn it in class 10 also. Now, what is power? So we have learned about energy. What is power? Power is basically something with respect to time. Someone needs to join this. Power is something with respect to time. Okay? So when you talk of something with respect to time, so what it is basically a rate, like rate of flow, rate at which energy is transformed is power. Okay, and unit of power is what is basically joule per second, and commercial unit of energy is kilowatt hour. That's it, that is what we call it as 1 unit of energy, 1 unit of electricity. This is what in which the bills, electricity bills, are actually billed to us. Now unit of electricity is 1 kilowatt hour. So it is basically 1 kilowatt of electricity being used for 1 hour. Okay, so 1 kilowatt of electricity into 1 hour is 1 unit of energy. So, sir has actually professor given a question also, like a 2 kilowatt heater is switched on for 3 hours. What is the consumption of electricity? So, let me solve this question for you. So a 2 kilowatt of heater is switched on for 3 hours. So multiply these two terms, 6 kilowatt hour. Okay, so what is the consumption of electricity? It's 6 kilowatt hour or 6 units. Now, generally electricity is billed as 7 to 8 rupees. So let's take 7 rupees. So rupees 42. So if you run a 2 kilowatt heater for 3 hours, it will cost you around rupees 42, depending on the price of electricity in your state or in your city. So this is that is why the people actually say ki don't use heaters. Heaters consume a lot of electricity. And compare this 2 kilowatt hour heater with 50-watt fan. So fan consume very less amount of electricity. Okay, compared to any other thing, fans consume very less amount of electricity. So wattage of something is very much important when you decide something. So basically these are the various sectors that require energy, that is domestic sectors like households, other things, transportation. What are the energy requirement in transportation, like running for vehicles, petrol, diesel? These are energy requirements in transportation. Agriculture, industry. Okay. So common forms of energy, we know about thermal energy. So this is very important because most of the time when we refer energy in our course, it is basically thermal energy or electrical energy. So thermal energy uses to meet the various industrial and domestic load. It can be converted to mechanical energy by using heat engine. Okay, so we will learn about these concepts later. Just as of now, so we can convert thermal energy to mechanical energy by using a heat engine. So what can be example of heat engine? It can be any engine like uh, the Rankine cycle, which we use in uh, power plants. Is basically also a heat engine. This boiler and steam turbine, all those things, and condenser. So thermal energy can be converted efficiently into mechanical energy. Quite true. Can be converted into mechanical energy with difficulty. Yeah, because the temperature is lowered here. High temperature, more conversion of energy. Low temperature, very very difficult to convert it into mechanical energy. Okay. Now we have chemical energy. So chemical energy is something that is stored in the elements of the matter or something. So it can be fuels or organic matter contains chemical energy, like we have gasoline, petrol. It has some inherent energy into it. Exothermic chemical reaction releases energy. So we have two types of reaction, endothermic and exothermic. So when we talk of exothermic reaction, it releases energy. Endothermic reaction, you need to give energy. And yeah, it's totally okay to convert it into electricity through fuel cells or batteries. Also batteries convert chemical energy to electricity, and it can be converted to thermal energy by combustion, like we combust the petrol and diesel to run the vehicles. Mechanical energy is basically something which is related to mechanical, like moving objects, changing of shape of object or something. Then we have electrical energy. So I think most of you are very much familiar with electrical energy. It's a very high grade of energy and it can be totally converted into work, okay, or thermal energy. And more than 40% energy distribution made through electrical supply systems. Yeah, is there a question or something? Uh, who is there? Did anyone said hello to, or anyone wants to ask question? Okay, so if there are no question, then I think we can go ahead. So if there are any questions, please feel free to ask. It should not be like I am not audible. Is it I am unmuted, I think. Settings. Samsung. Hello, am I audible? Okay. So I am very sorry to you guys that I was not audible and I could not read your messages also. Okay, it's okay. So in the starting also I did ask this question that I am audible or not. I think nobody replied, so I took it as that key I am audible to all. Okay, no problem. It's okay. So I think not audible. Not audible. Okay, okay. So, okay, I will do what I will do. I will take a recap of whatever I taught in the last 15 minutes. So that will also help you grasp the concept once again. Okay. So, somebody who has joined new, who has joined recently. So, welcome you all again to this live session of the course Solar Energy Engineering and Technology. So here we will talk about this solar energy concepts and various applications also. And this course is basically taught by Professor Pankaj Kalita. He is from IIT Guwahati. And I am Rohit. I am a research scholar in IIT Bombay. So I will be taking this live session and will taking the questions from you all. So these sessions are basically planned to have an one-to-one interaction with the students so that you guys can raise your doubts, I can answer, and don't worry, most of your doubts will be answered in this live session. If anything is not answered or needs more discussion, then we can carry it to the next live session also. Okay. So till this time, whatever I have discussed, basically I have gone through the various concepts of the energy, power, what is energy, what are different types of energy, because the main reason of this is most of you cannot be from science background or engineering background. Somebody may be from this humanities background like arts, law, or anything, so he want to learn about this uh, concepts. Yeah, Suruchi, I haven't shared my screen yet. I am just giving an introduction. It will be visible to you. Okay. So, are the slides visible now? Yeah. Okay. So, let us move to the slides. So, it will be basically better to have a talk. So, main problem is with this Google Meet now, ki you cannot see when you teach with slides, you cannot see the this in call messages. So that is very difficult. So what I will do, I will give a break of 1 or 2 minutes after teaching 10 minutes, then I will take the questions from here. So whatever question you have, please put it in the in call messages there. Okay. So let me start from beginning. So basically we talked about this energy thing, like what is energy is basically everybody know it's the capability of to do work. Okay. So basically, energy is the most basic infrastructure input for economic growth. So if a country has a high economic growth like US, it will consume more energy. If a country like India or Bangladesh has a less economic growth, it will consume less energy. So I will give you an example also here. Like per capita electricity consumption of India is around 1 unit, like 1 kilowatt hour, and for this US, it is basically 20 kilowatts hour. So it is 20 times more than us. So unit of energy is basically joule, which most of you is familiar of in class 9, 10 itself. Power is basically rate at which energy transferred or transformed. Rate, what is rate? Rate is something energy with respect to time. Okay. So unit of power is what? That is joule per second. Commercial unit is kilowatt hour. So I solved this question also. 2 kilowatt heater switched on for 3 hours. So we get rupees 42 as some bill. Okay. And these are the various sectors in which energy is required. So common forms of energy we talked of, like thermal energy, which can be converted to mechanical energy. So higher the temperature, easier is the convenience to convert it to mechanical energy. Okay, so if the temperature is low, it's very difficult to convert the thermal energy to mechanical energy. And we have chemical energy. Better example is fuels like gasoline, diesel, or batteries. Then we have mechanical energy, which is through moving of objects or something. Then we have electrical energy, which is basically a high grade energy, and more than 40% of energy distribution is met through electrical supply systems. So these are very convenient because electrical energy can be converted to work or thermal energy very easily. 100% conversion is also possible. So I think no questions as of now. Then we can move ahead. So it should not be like, please ask questions, any question if you want. It should not be like I am only talking and you are listening. It should be a one-to-one interaction. Any question, any doubts which you want to discuss, please raise your doubts. Please raise your doubts. Okay. Then professor basically talked about Aristotle, Greek philosopher. So he basically said that it is clear that there is some difference between ends. Some ends are energia. Energia he is referring to energy, while others are products which are additional to the energia. So he is saying that we need two things: energy and products that to make our life. Very beautifully he has put the pictures. And Nicholas Tesla, he is the most genius inventor or scientist ever happened in the world. So he's in the level, you can say him in the level of Albert Einstein. Okay, so these scientists are all very great scientists. So he invented this induction motor, and this motor has actually changed the way we utilize the electricity, okay, and generate electricity. So basically this is his core. uh, all the revolution, agricultural, whether it's agricultural revolution, industrial revolution, or anything, is requirement of energy is always there. Wants to join? Yeah, the recording is going on. So he has actually, professor had discussed the progress of energy use from 1900 to 2009. So you can see the energy usage. It's basically exajoules. So that was basically in the start of this century. At the start of this previous century, 1900, it was less than 50 exajoule, and now in 2009 you can see where it is. The growth has been exponential. It's not a linear growth, it's exponential growth. So that is very high growth. Okay, and let's move forward. So world energy scenario basically talks about the energy consumption of the world. So more darker is the circle or color, more intense is the energy consumption. So if you compare US with India, it's 2258 for US. Mind the units, it's a million tons of oil equivalent. Okay, so all the energy are converted to the primary form of energy, and basically compared with, uh, to have a comparison. China's energy consumption growth is 3.7%. So China basically has a higher amount of energy requirements for this consumption of electricity or energy because of industrialization in it. All other things which we classify. So you can see that the requirement of oil is almost a linear trend, or maybe it has been stagnant in the last projection for 10-20 years. But see the amount of renewables. In 1970 we didn't had any renewable. Now we have around 3 to 4% of all the energy as from renewable. So that is a huge amount of energy or electricity, whatever you can say. And still, the main issue is that fossil fuels like oil, gas, coal share 80% of the total energy consumption globally. So when we talk of this energy consumption, so mind it, this is primary energy consumption. It's not the electricity. Okay, electricity is secondary energy. So the question can arise here, like you guys can ask, what is primary energy? What is secondary energy? So primary energy is something that energy derived from the in the raw form itself, like coal. Okay, like fossil fuels. These are primary sources of energy. Secondary sources are that you convert this primary energy to some other form like electricity. So you generate electricity from coal. Coal itself is primary energy, electricity is secondary energy. So this graph basically tells about the world energy scenario in 3 different decades, and what are the effects of fossil fuels. So you can see the effect here, the rise in the recent global monthly mean CO2 emissions. So you can see the parts per million, and CO2 emission is growing. So it was in 2015 it was 400, now it has reached almost 410. And this is showing the temperature distribution, and as per IEA report, the global CO2 emission is estimated to be 32.6 gigatons in the year 2017. That is a very huge amount of CO2. 36.2.6 gigatons in a single year, and the safe limit was 350 ppm in the atmosphere. Now it has reached 410 ppm. So you can see. So Rawat has actually asked. Rawat has asked, "Sir, which is the best experimental setup? Is easy to build without funding option, such as solar water heater, solar desalination, solar dryer, solar power grid research." So basically, funds. Why we require funds? Funds are required to build a setup which has a more efficiency. You can build a solar setup with a simple mirror and a curvature also. So that will also function as a solar setup. So what for what requirement? Uh, what is the main requirement for which you needed some solar devices? So that is, if you need solar devices to produce electricity, a good amount of electricity, so that will require crores of money. You cannot do it in thousands of rupees. But if you want solar energy for solar devices for heating water, so that you can do in thousand. And probably you can build a solar water heater on home in rupees 5,000 also. You just have to concentrate the light on some pipe and pass the water through this pipe, that will gain the energy and get it stored in some drum. That is, but it won't be such efficient. The efficiency will be very very low. You won't be able to utilize most of the sunlight. That will go as a unconcentrated portion. Okay. Any other question which you guys needed me to answer? Thank you, sir. Welcome, Rahul. Okay. Any other question? No questions. Let us talk about this. Yeah. Who is this? Suruchi. Yeah, Suruchi. Say. Mm-hmm. Mm-hmm. Sure, Suruchi. I will show the complete assignment, but these assignments are from previous run of the course. These are not from the recent run. So these are from week zero previous run of the course. Previous. So this course is actually run in the last year also. So those assignment question which you are getting in this year are not the same as the previous run of the course. Okay. Week zero and previous run, previous year. So I think we take care that ki people doesn't get advantage due to these assignments. Okay. Okay. Uh, so okay. So when you see the CO2 emission in the December 2018, it was 40408.94. Now the December 2019 data, it was 412.02. So you can see there is an increase in the CO2 emission. But there is a catch. I will tell you the catch. So main catch is that key for this short term you cannot say that key CO2 emission has increased because CO2 emission goes like this. You see the graph, CO2 emission goes like this. Okay, so it increases, decreases, increases. But if you compare a range of 2 or 3 decades, so a linear increasing trend is. So this is more important. This increasing trend is more important. So you cannot say for a single year, but still it gives an idea that yeah, CO2 emissions are increasing. So that is a cause of concern. We need to think about this CO2 emissions that are basically coming from this fossil fuels. So if we see this fossil fuels or the production of fossil fuels, so this is a graph and it has some future discoveries, production, and some other data also. So I think this graph you can easily understand by going through. Okay. So it basically talks about the proven results, future discoveries, and this BBLS is billion barrels per year. Okay. And this is the cumulative production. This is the proven reserves. So this much we can tap, but yeah, still this much has to be discovered yet. So it is not that key everything that is discovered as a fossil fuel reserve can be utilized. So there is some feasibility study also whether we can utilize it or not. So these things has to be taken care when we talk about fossil fuel utilization. Now the main question is why renewable? Why renewable in a broad sense? So climate change, which you can see in the previous graphs also, like we have climate change. We had energy crisis when these Gulf countries stopped uh, selling production of this fossil fuels, so the price rose or they stopped giving oil or they lowered the production. Energy security for a country is very important. Like India, most of the energy in the terms of fossil fuel is actually imported from the Gulf countries or Russia. So that is very important. Maybe that these countries go as adversaries and stop the supplying of energy. So we as a country with 1.4 billion people cannot uh, take the risk or chance. So we need to have some energy security. And where does this energy security can come? It can come from the renewable energy. The last point, which is very important and is the main focus of all the agencies in the world, is sustainability. Whether we can sustain this energy security or energy usage which we are using. So when we talk of sustainability, the main thing which is getting reminded is basically whatever level of usage of energy which we are using, we need not increase it for our future generation also. So they, with their capacity, they are easily met the requirement. But this energy security has energy usage has to remain flat. Okay? So sustainability can have many meanings. It basically derives its definition from the a report by UNDP in 1987. I forgot the name of the report, but it was, I think, Brookland Commission or something. So please read the report. It was a very good report on sustainability, and still all the decisions are basically taking in mind that report and other conferences which we uh, have on climate change. Now we can talk about what are the different alternatives. So alternatives can be solar, wind, geo, hydro, bio, and tide. I think most of you are very pretty much familiar. Solar is with solar power, sun power from sun, wind is through wind. Geo is energy derived from earth. Geo is a word for earth. Hydro is something that is related to water. Bio is something biomass, and tide is basically tidal energy, ocean energy. So these are the trends of the energy in the 40-50 years. So you can see the share of renewable energy is growing at rate of 7.1%, and this global renewable energy capacity total 2378 gigawatt in 2018, but it must be more now because it's a 2018 data, and most of the world countries are actually focusing on renewable energy. So in the upcoming decade, you will see that most of their energy requirements is basically fulfilled through renewable energy. The main thing is capacity factor. So we will talk about this capacity factor when we talk about solar. I will give you an example. Like a plant has a capacity of 500 megawatt, but it cannot produce 500 megawatt all day. A solar plant. I am talking about solar. Why? Because in night we don't have sun. So where do we get the power? We cannot get the power. Okay, you guys are understanding now. So in night we don't have any sun. So whatever power we can produce in the 8 hours of the day. So its capacity will be one third of the total capacity of a coal power plant. So coal power plant have generally high capacity factors. Now we have the energy security scenario in India. So most of energy is coming from coal, then gas, then lignite, and large hydros. Overall energy security scenario is basically coal is still the king. Simple thing. Coal is still the king. Most of our electricity is coming from coal. We can, if we are thinking of something as a energy, then we have to take in mind that key, uh, like if we are utilizing energy for electricity for these vehicles, electric vehicles, but most of the electricity is coming from coal itself, so it will have the contribution of CO2 from the power plant itself. Until and unless we shift totally to the renewable energy, or we shift a majority of our production to renewable energy, we cannot say that we have achieved a sustainable lifestyle through electric vehicles or anything. Then we have installed capacity here: central sector, state sector, and private sector. The thermal increased by 3.57%, renewable increased by 137%. That's a pretty good news because most of the increase is being seen in the renewable. Now the question is, why solar? This is the main question. Why solar? So there can be many: solar, wind, and tide, and geo energy. Why solar? So it's basically a clean source of energy. No emission is there. We use a photovoltaic cell. Sunlight get into it and it produces electricity. No emissions. Whatever background emissions from the production of the solar photovoltaic cell, if those are ignored, then there are no emissions in the operation of the solar energy. Second thing is availability. Very much, pretty much available for a country like India, because we are a tropical country. We have a lot of solar energy. Affordability also. But now why? Because earlier the solar energy cost was very high. It was not feasible for power plant company to set up a power plant, but now it has come down to as low as 2 or 3 rupees per unit for the power generation company. Most advantage is there because no, we don't have to purchase this coal. We don't have to purchase a boiler or steam turbine. So everything is removed from the system. You have a solar photovoltaic cell. You maintain it, get the sunlight, required sunlight, and get the electricity. Government support is there because government is giving a lot of subsidy to promote the renewable energy, especially the solar things. So these are the main key benefits, and this is the price history. So in 1977, 1 unit of electricity from solar cell costs $76. Now it is as low as 0.30. So you can see this is basically very important realization in the development of solar cell, silicon PV solar cells. Okay, so there is a Swanson law also which says that the price of solar photovoltaics modules tend to drop by 20% for every doubling of community saved volume. So more is the production, more lower is the price. This is basically a supply demand market play. When you have more production, the price will go down. Okay. At present, cost decline by 75% about every 10 years. It is named after Richard Swanson. So this data gives uh, good view about the installed solar energy capacity throughout the world. So India is here. I think it's the 2018 data, but India has catch up pretty fast. I think now we are producing more than 100 gigawatt from from different types of energy, and more than 40-50 gigawatt from solar. Okay, I don't have the. I think it was 45 gigawatt from solar. So these are the top 10 states with maximum solar capacity. Karnataka is leading and Punjab is the lowest. Then we have this generation. So most of this generation is coming from China, then US, Japan. I think India has catch up pretty fast. It must be to second or third position. So if we summarize this slide, it's basically we define the energy and then show the requirement of energy, world energy scenario, Indian energy scenario, global trend of generation of renewable power, trend of generation of solar power. So these things were actually utilized to get a good view about the utilization of solar energy. Okay, I think most of the concepts have been clear to you guys. So let me pause a little and take your questions. Okay, so there is a question from Raval. He said that how to remember latitude, longitude, azimuth angle, declination, and process to find a complete solar intensity analytical process. Is there any trick or can you give us any hints for it? So yeah, Raval, basically you need to understand these angles. Just don't memorize them. What I have done in my master's days that okay, I try to understand what are these angles, why these angles are required, and those when you understand these angles, the big formulas which you see, I don't think you need to memorize those big formulas. The small one you can memorize, and NPTEL also doesn't force a student to memorize a lot of big formulas. Generally, if any question is asked, the big formulas will be given to you, and okay, so don't worry about that. We also don't focus on putting mugging. Okay, we generally focus on making the things understandable to the students so that they can have a good understanding, good view point on the things which is being discussed here. Okay, so is there anything, any other questions? sir, is there any Bhayani Naitik Jignesh has asked, is there any research in solar engineering? So let me be clear, Naitik, a lot of research is there in the solar engineering field. Lot and lot of research. You don't even imagine the quantum research which is going on this field. You haven't heard about the perovskite based solar cells, monocrystalline, polycrystalline solar cell, amorphous silicon, crystalline silicon. So these things are basically like even the India has achieved last month. India has made a perovskite based solar cell that has uh, what you say, a lot of energy, a lot of efficiency, like some 26% efficiency they have reached through research. So it's in research phase. It will take a lot of time to get it transferred to the market, but yeah, in the recent 5 to 10 years you will see a lot of new technologies in the field of solar engineering. And don't worry, we will be discussing all these things in our this coursework course. So go through the weekly lecture slides, you will find all those things. Okay, so Ruchi has asked, could you please provide some hints for the last question of assignment 1? Assuming black body radiation of the temperature to be itna, if the radius of sun is itna, then mean earth sun distance in will be. So yes, Suruchi, I will give you a hint to this question, but basically this question is uh, your understanding of different formulas and concepts. So this is pretty if you combine two three concepts you will get the answer of this question. Okay, so basically the temperature of sun you know, and the energy coming from the sun you know, radius of sun you know. So you can easily find the mean earth's sun distance, you know, the solar constant here. So this can be used to find the earth sun distance. Okay, so I will tell you also how to calculate it. Otherwise I think I should not, this is from question from assignment 1 na. I should not solve it, but I will give you a hint. Okay. So, any other questions? Okay, no questions. Then I think we should take a break of 5 or 7 minutes. So, because you guys must be bored of having a 1 hour long lecture on the solar engineering, the basically the applications of the solar engineering and the concepts and definition. So let's have a break of 5 minutes and then we will assemble it by 7, 8, 5. Okay. Yeah, Suruchi. Okay. So, okay, so I will give you a hint. Try to search for solar constant. Okay, the solar constant for Earth. So its value is 1367 watt per meter square. Okay. So you know the temperature of the sun, 5777 K. So you can get the energy sigma into T4 from Stephen Boltzmann constant. You get the energy. Then that energy has to be transferred to Earth. Okay. So through that you can calculate the mean Earth sun distance. What is OTEC? Simi has asked what is OTEC. I don't know, Simi, what you are talking about. Can you write the full form? Ocean thermal something. Okay. So this whatever it is, OTC, I don't think OTC is a standard terminology used for ocean thermal energy. It's ocean thermal energy conversion. Basically, we convert the there's some you will get to know about these things. So there is Edinburgh duct also, the waves converter also. So these are different types of devices that convert the ocean energy to electricity, to movement of blades. So I think this is not so will be this won't be discussed in this course, because this course basically focus on the solar energy engineering and technology. But to get an idea about these things, also thermal conversion technology, you can, there was Edinburgh duck and this Perkinber or something, I don't remember the name. So these are some of the things, some of the devices that is used to convert the ocean thermal energy. Okay. So it's no, it's talking about ocean thermal energy. Okay, so basically it's a conversion of the upper layer has a high temperature, the lower layer, the lower layer has a high temperature because it is insulated through the layer of water above, and the upper layer is cool. So using these two temperature difference, you can actually produce some electricity. So there are some devices, I don't remember the name of those devices, that can be utilized for ocean thermal energy conversion. So yeah, let's have a break for 5 minutes. We'll meet at 8:06. Okay, so once again, welcome back to all of the students here. So I think most of you have got some snacks and drink some water. And are you guys feeling fresh? Okay, so what I say, let's not make it a one-sided conversation where I am teaching the slides and bombarding you guys with the facts and different definitions. So let's make it a two-way. Okay, so you guys ask questions. Anything you want, just put it in the in-call messages like Suruchi and Simi and Rahul has asked and Diganjit Rahul has asked. So I think these things are very important to discuss and to get a good idea about the course also. So now I will stop here the discussing about different slides and I will move to the discussing of the um, assignment questions from the previous run of this course, and these questions are from week 0. Okay, it's not week 1 questions, and these are from previous run of the course. So uh, this is basically I am taking a week back because to make sure that you guys doesn't get an advantage with the other guys with these assignment questions. Okay, but still you guys are uh, can ask the questions and I will give you a hint about how to solve those questions. If you don't understand anything, we can discuss it here. Okay, so I think we can start it from here. So I will take up the assignment question. The related concepts will be discussed from the slides. Okay, so that will make it interesting also. So the first question is basically asking about the portion of the radiation spectrum emitted by sun in the wavelength between zero point 0.4 micrometer and zero point 0.7 micrometer is called. So when you see a sun radiation, so it's basically like this. This is zero point 0.4, this is zero point 0.7, and this area is basically belongs to visible light. So visible radiation is the correct answer. So whatever beyond this visible region is ultraviolet radiation, and whatever here is infrared. Okay, so that's how ultraviolet and infrared are different. It's baby pure, sorry, here it's R E, more wavelength, less energy. Okay. Another thing is that what is radiation? So radiation is the mode of heat transfer in which there is vacuum. The energy transfer through vacuum in the form of a wavelength. Okay. Now you know the IR and UV. So let's see if there are anything in the slides which talk about this. Nothing, nothing in the slides. Questions, questions. Now the next question is ki, which of the following expression relates the energy of photon with wavelength lambda? So it's basically energy is related through h c upon lambda. Lambda is wavelength, c is the speed of light which is 3 into 10 k power 8 per second. H is Planck's constant which is 6.626 into 10 to the power minus 26. So this is the term which defines the energy associated with any wavelength. So if you have a point 4 micrometer wavelength, you can put the values and calculate the energy associated with it. Okay. So this term can also be written as mu, that is frequency h mu. So this is also energy. Now I have a trick question for you. Is calculator a solar power device? Anyone? The day-to-day use calculator which you use in your houses or in the shops, are those devices solar powered? Let's see the answers what people are saying. Yes, sir. Okay. So Rahul and Janvi has answered yes, and rest of all are unconclusive about this thing. Natik has also answered it. Yeah, it's totally correct. It's a solar power device. So you can see very small cells in the calculator. So those small cells are basically capture the solar energy, charges the lithium battery in the calculator, and provides the required power to run the calculator. So calculator can go on for years because of this. You don't need to charge your devices. Okay. Another question is that what can be some solar power devices? Think. What can be some solar power devices? Think and answer. Can you name some? So let's see how many. Yeah, solar heater. Netik can answer solar heater. Very good, very good. Janvi, solar heater. Yeah. Apart from solar heater, anyone? Emergency lights. Okay. Because emergency lights are charged from solar. Solar dryer. Very good. Very good. Solar cap fan. So in toy. Okay. So in toy, he's saying some solar cap fan. Yeah, it's okay. Those are also solar power devices. Street lights. Very good and smart answer. Solar dryer is very good answer. And I am surprised nobody has mentioned about photovoltaic cells. Those are also solar powered, na? They convert the electricity directly to PV panels. Yeah, that is what I was expecting. Okay, it's good that you guys are very much familiar with the solar technology, so that will make it make the course much more interesting. Mobile chargers, Ruchi has said mobile charger. Yeah, nowadays mobile charger are coming that operate solar powered. I don't think so. But yeah, mobile charger can be engineered to solar cooker. Very smart answer. Lakshmikant from Lakshmikant. Solar cooker is a very smart answer. Solar pumps is also a very good answer used in the villages. Okay, so let's move to the next question. So in next question we have an hot object of temperature T1. So we have a hot object of temperature T1 is placed in vacuum chamber. This is a vacuum chamber. This is the object. Vacuum chamber has a wall temperature of T2. The hot object cools, so it will cool, it will give away the heat. As a result of heat exchange by, basically we have three modes of heat transfer. What are the modes of heat transfer? One is conduction, when these two bodies touch each other, then they conduct heat through electrons, movement of electrons. Okay, that I say. Convection is basically natural currents. So in water or any fluid, so if there is some layer which is hot, will transfer the heat to layer which is cold. Then we have thermal radiation. When there is no medium present, then the heat transfer will occur through thermal radiation, which is correct answer for this. Evaporation. Evaporation is totally different concept. It's basically if there is any fluid or water, so something which is transferred to the gaseous form is evaporation. So evaporation doesn't transfer heat, it actually takes away the heat. Have you heard about thermal? Have you heard about conductivity? So anyone heard about conductivity and heat transfer coefficients? I think these terms are very much familiar with those who have mechanical engineering background. So yes, sir. Heat transfer in solid body. Yeah, Naitik has answered. Conductivity is heat transfer in solid body. Basically, when you have conduction, then the conductivity plays an important role. It is basically the heat transfer in the direction of heat flow per unit length. Okay, and per unit area also. Rahul Adhikari, yes sir. And convection is basically when you talking about heat transfer coefficients are basically used when you talk about convection. Okay. Now we have this. Which of the following law provides the rate at which heat and energy radiated by a black body? So mind it, it's talking about black body. So black body, how much is the epsilon value of black body? Emissivity value 1. It doesn't emit anything. It absorbs everything at a given temperature. So it is basically a Stephen Boltzmann law E equal to epsilon sigma absolute temperature in Kelvin to the power 4. Okay. So for black body, this epsilon value will be 1. So it will be sigma into T to the power 4 is Stephen Boltzmann law. So first take a look at this formula for few minutes. I want you to focus on this formula. And in the meantime, let me see if the recording is going on. Yeah. Fourier law. No, Natik, it's not Fourier law. Fourier law is basically for conduction. In radiation, it's Stephen Boltzmann law. Newton's law in convection. Fourier law in conduction, Stephen Boltzmann law in this radiation. Booker's law is basically in, I think, diffraction or something. I am not sure about this law. Okay. So first take a look at this formula E equal to sigma E4 into epsilon. Then we will discuss this graph. First take a look at this formula. So if I plot a graph between E and this temperature, how will be the what will be the nature of this graph? Can anyone say what will be the nature of this graph is if we plot a graph between energy and this temperature from this formula? You can see the graphs here. What is the nature of this graph? Nobody? So when you see this graph, you see that we have t ke power 4, absolute t to the power 4. So it will follow a curvilinear shape. Okay. So you can see the curvilinear shape here. And as the values of E are increasing, the shape is actually increasing more. The slope is increasing. Okay. So here we have less slope, here we have more slope, more slope, more slope. And this is the black body radiation E equal to 1. Okay. So whatever power it emits at this temperature, so you can just draw a line from here for black body and draw a line from here. You can see how much power it will emit at 3000 Kelvin. Okay, a black body will emit how much power. These graphs are very much important. Okay, and how these graphs are made? Just put the values of E in the equation, plot the for different temperature for 500, 1000, 1500, 2000, and so on. You will get the E values. Put the points and plot these curves. Okay. Exponential, yeah. Karthikeyan and Suruchi has mentioned exponential. Yeah, yeah, yeah. It's not you cannot say it exponential, but it's curvilinear type of shape. It can be called exponential also. Yeah, for curvilinear shape, they generally use the word exponential. But exponential is typically something which is related with exp power. Okay, so curvilinear is a better word. Now we will talk about a very important concept, kinematic viscosity. It's a very important concept, and we will put. I have put some 2 3 slides on this just to make you familiar with kinematic viscosity, dynamic viscosity, fluid density. Okay, and how they vary with temperature and other phenomena. So it's just a simple mathematical expression where we see kinematic viscosity written by nu equal to dynamic viscosity upon rho. Okay, so this one is correct. Dynamic viscosity upon fluid density is kinematic viscosity. So what's the difference between these two? Viscosity, you know now, viscosity is ability to resist movement of fluid. Okay, so there will be resistance when a fluid will move. So more thicker fluids have a high viscosity. Thinner fluids like water has less viscosity, petrol has less viscosity, honey has more viscosity. Now problem is with kinematic and dynamic viscosity. Dynamic viscosity is something when it's tending to move. Okay, not moving, tending to move. Kinematic when it's moving. So let's have a comparison between these two. One is absolute viscosity. Dynamic viscosity is basically absolute viscosity known by quotient of absolute viscosity also. These are known by this. It's basically shear stress upon shear strain. It's dynamic viscosity upon density. It's written by mu and it's written by nu. These are the units. You can see units in newtons second per meter square. Here in meter square per second or stroke. It has no dependency on the density of fluid, but it has a dependency on the density of fluid. Okay. The viscous force is dominant here, but the viscous force and inertia both are dominant here. Okay. Now let's see the variation. So take a look at these graphs. Okay. So it's basically these graphs. You say 1 2 3 4 graphs are there. So let's ignore this graph. This is not for our use. It's dynamic viscosity, it's kinematic viscosity, and density. Okay. So this talk about a lube oil fraction with increasing fraction of V by V. It's saying that the density is increasing. Okay. Density of the lube oil fraction is increasing So if we see the dynamic viscosity with increase in density and the percentage of low fraction, the dynamic viscosity is also increasing. And generally, kinematic viscosity is mu upon rho. So this is also increasing, which is seen here. So these are following a similar trends, but this is not always that it will follow the similar trend. There may be time that this is increasing, but this is basically decreasing or increasing at some other rate, kinematic viscosity. Okay. See if there are any questions. No questions. Okay. Now another question is Reynolds numbers. So Reynolds number is basically very important number when you talk about fluid flow. It defines the nature of the fluid, like laminar nature or intermixing nature, intermediate nature, or turbulent nature. So Reynolds number is basically a ratio of inertia force to the viscous force. Okay, so correct answer is answer B. Now, if we focus on question 7, I want you guys to read the question 7 first, then we will discuss it because I have put a slide here also, so it needs a discussion, you guys. Because if you understand this concept, you will understand a good grasp a good understanding of the thermal when we discuss the thermal energy or thermal engineering. Okay. See if anybody has any issue. Okay, so let's see. No questions. Option C. Janvi has been said option C. So no, Janvi, it's not option C, but yeah, option C and option D are very much related to each other. I will show you how. But the correct answer is option D, internal energy. So it's saying that there is a closed system. No, no, what is closed system? No energy and mass can transfer through these systems. Difference between heat added, sorry, and no mass can transfer, energy can transfer. Okay. For isolated system, no energy and mass can transfer. For heat added, so we have added a heat Q and work done. The system has done some work. Okay. So let me tell you in simple words. Let's forget Q and I have given 10 joules of energy to this system, and this system has actually performed 8 joules of energy, joules of work. So what is the difference? 10 minus 8 equal to 2 joule. So there must be 2 joules somewhere, because as per the conservation of energy, energy cannot vanish, because it has taken 10 joule and given work of 8 joules, so there must be 2 joule in between. So 2 joule is actually what this 2 joule does. It increases the energy, internal energy of the system. Okay, it stores the energy. So that is what it is saying, internal energy. And this internal energy, how does this internal energy change is detected? It is a function of temperature. So as the temperature increases, the internal energy is actually increases also. So because it is, why temperature is not a correct option here, because it is talking about energy. Heat is energy, form of energy. Work is also a type of energy. So we have to give the answer in terms of energy, that is internal energy. Now if we see the slides here, simple, this is a closed system. No mass can transfer, but heat can transfer. So it has taken a heat Q and done a work of W. So Q minus W is the remaining heat which needs to be identified. So it goes into changing of the internal energy. Okay. This is the basically equation. It's also called conservation of energy principle also. So Q is the heat transfer of the system. Work is work done by the system. Del U is the change in internal energy. Okay. Now this is the question which you need to answer by yourself. I will not give you the answer. And let me see first if there are any questions. Okay. So guys, please do this question by yourself now. I want answers from you guys. I am giving you 5 minutes for this. Please solve this and give me the answer. I have mentioned the formula here also. Please solve this. Then we will talk about this question. Mm, Option A, option A. So, okay, Natik has actually said Suruchi 71.76. Rahul has said option 1. Natik 96.25. Lakshmikant has said option B. Sunil has said option A, option A, option A. So Suruchi has said 71.76. Why 71.76? How have you obtained this? Janvi has said option C. I think option C is not the correct answer. Okay, let me solve this. We have to convert Celsius into Kelvin first. Yeah. So this is the main catch here. So C has actually got the correct answer. Most of you guys have actually said option A, 96.25%. But in actual terms, the for applying the formula, you need to convert uh, the source temperature and sink temperature to Kelvin. Okay, these are absolute temperature. So let me solve it for you guys. So source temperature, let us say S dash. It's 800 degrees Celsius. It's 1073 Kelvin. Sink temperature, that is, this is T1, this is T2. 30 degrees Celsius is equal to 303 Kelvin. Now just put it into the formula. Okay, so option B is the correct answer. Option A is wrong because most of you guys will be putting this directly. It's not a direct. Whenever you talking about efficiency, make sure the temperature is in absolute values. Okay. Good, Suruchi. You have done it correctly. Okay. And those all of those who have obtained option A, Sunil, Siru, and who else has obtained option A? Okay. So anybody who has obtained option A is actually correct. Now we move to the next question. This is a very interesting question. It says that which of the following instrument is used to measure the temperature. So we have manometer. You know the manometer. These are tubes like this. Okay. We have mercury here. Somebody wants to join. Let's see. So we have tube here, and we fill this tube with mercury. Then it measures the pressure basically. Okay. Thermocouple is something which is used to measure temperature. Bourdon tube is used to measure pressure. So this is the Bourdon tube. I will discuss this. Anemometer is used to measure wind velocity. So the correct answer is answer B. Okay, thermocouple. Now most of you won't be familiar with the term Bourdon tube. So Bourdon tube is basically a kind of tube, elastic tube. Okay, and there is this connection with the toothed quadrant. There is a pivot and a linkage that connects to this elastic membrane. So whenever pressure is applied, when you apply pressure, it will actually compress. So it will move to this direction. Okay, it will compress, then it will move this. It will move to this direction. And whenever pressure is released, this tube will expand. So it will put the this thing in this direction. So that's how this dial actually moves up and down. Okay, this is the concept of Bourdon tube pressure gauge. Sir, in this question we have opted for thermocouple option only, but after submitting it showed that answer is incorrect. The right answer was Bourdon tube. Yeah, the right answer is Bourdon tube. I have also submitted it and checked it. The right answer for this question is actually thermocouple. Okay, Bourdon tube is wrong answer. So please write this. Please report this in the discussion forum. We have this discussion forum where NPTEL people take a look at these questions. So they report this to the NPTEL and it corrected. So please report this question in the discussion forum so that a correct answer can be obtained. The correct answer is thermocouple. Thermocouple is used to measure temperature. Okay. Now the last question here. I will also not solve this question. Okay. I will give this question to you guys. Please solve this question. The air is blown over a hot plate. There is a hot plate, okay, which has a cross section of 50 into 60. Air is blowing to this hot plate. The temperature of this hot plate is 220 degrees Celsius. The air temperature is 20 degrees Celsius and the heat transfer coefficient, that is H value, equal to 25. Please solve how much is the amount of heat loss from this plate. Okay. Please solve. I will give 5 minutes to you guys, so you guys can solve it. Please solve this question. So Sunil, Naitik, Rahul, they are actually doing it good. But make sure to convert the temperature values in Kelvin. Okay, even if it's temperature difference, you need to write it in absolute values. So let's solve it. Let's see how many of you have solved it. Okay, Rahul and Naitik, these two people have tried it, and Sunil also tried it. Okay, so let's solve it now. So we have this heat loss equal to small h into area into del T. We have small h equal to 25. Area is 15 to 60. Basically, we are converting this area into meter square. Okay, into del T. Del T is basically 220. Please write it in Kelvin terms. I am writing it in degree terms, but you guys please write it in Kelvin terms. So it's basically 25 into 0.3 into 200. The answer will be 1500. The correct answer is answer B. So those who have got option B, so Sunil, Rahul, option B is correct answer. Okay, that is 1500 watt is lost. So I think we have discussed a lot and discussed the various concepts, basic concepts related to energy and all those things. I think you guys must have got a good understanding about these different heat transfer phenomena, and we saw the numericals also. So here is the last slide. I think you guys will be very happy that the session is concluded after 2 hours. But yeah, it was a lot of interesting things, pretty interesting with discussion with you guys like Naitik, Rao, Suruchi. So yeah, interactions are always welcome. So you can always find me at this email ID. And even if you have any queries, please post it in discussion forum. So that will benefit all the students. Okay, and I will upload these. All sessions are actually recorded, so even if someone has missed this session will be uploaded on my YouTube videos. and the links will be shared in the problem solving session link which you have got as a mail. So please, you can also follow it from there. So when you log into your NPTEL, there will be problem solving session tab there. Click on it, you will go to a link. In front of my link, click on the YouTube video, you will get this video. Okay, so every session is recorded and it will be uploaded for the benefit of you guys. So thank you all, thank you once again for joining this interactive session, and we will meet on the next Monday. If there are any difficulties or any question you want to ask, please feel free to ask me. Okay, otherwise I will end this session. Thank you all, thank you once again. Yeah, so Natik has said it correctly. So he has actually opted for 1500, but the right answer was showing 2500. It's the wrong answer. The correct answer is 1500. Please raise this also in the discussion forum. Yeah, Suruchi, there is a session tomorrow as well. Basically, we have two TAs for this course. So we have two sessions. So anyone can attend any of these sessions. The same thing will be taught tomorrow by the another TA. Okay, so he will handle the tomorrow session. You can attend any of these two sessions. Okay, or if you want, you can attend both the sessions. That is totally fine. So I think I should end the session now. A link for the recording will be available in the problem solving tab of your, when you log into the NPTEL or SWAYAM course, you will see a problem solving there. So let me show you guys actually, so that will make you SWAYAM. So you can see my screen, SWAYAM. 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 So here it's not showing. There will be a problem solving session link here. Let me show you from some other. So this is the previous run of this course. You can see the problem solving session here. Problem solving session. You click on this, you will find this. So these are the YouTube links. Okay. Click on these YouTube links. You will go to the YouTube where you will find the. Okay. So these are from the previous run of this course. Okay. So you can find me. You can also subscribe the channel if you want. So you can get whenever a video is posted, you can get a notification for that. I think for today it's totally okay. I think a lot of things have been taught. So thank you all. Thank you for attending the session. We'll meet in the next Monday.